Okay, in our previous video, what we did was we took a cubic polynomial, which was of the form, and I use the variable z to write it down, z cubed minus 9z squared plus 21z minus 5 equals 0. And we performed a change of variables, a rigid translation of the graph, if you will, and turn this into a new polynomial, x cubed minus 6x plus 4 equals 0. And this polynomial will be the subject of our investigation for this tutorial video. And basically what we want to do here is implement something called Cardano's method for solving the quadratic. And so Cardano's method looks kind of similar to what we did before, but instead of having a change of variables of the form that looks like a variable plus a constant, Cardano's idea is that we replace the variable x in this equation that I've circled with a new variable. So we think of x equals u plus v, where u and v are both variables. Now it looks initially like that's going to wind up causing you some problems, because it looks like you're going to wind up with two variables instead of one. But the two variables are not going to be independent of each other. So the idea for Cardano's method comes from this, that if we take u plus v and cube it, that with the binomial theorem becomes u cubed plus 3u squared v plus 3u v squared plus v to the third, which can be written as u cubed plus v cubed. Okay, it almost looks like something cubed. It's the sum of two cubes. Plus 3 times a common factor of uv. There's a u here and a v here, and a u here, and at least one factor of v there. So we factor out 3uv from that pair of terms, and what's left is u plus v. So if we make our change of variables, then in fact what happens here with our original equation, well, let's make this a little bit smaller so we don't wind up losing. Let's see, on this page. Okay, I think I'm organized enough now to do this. So we take our equation up here, and everywhere we see an x in this equation, which I'll put a star next to it so I can refer to it as equation star, everywhere we see an x in equation star, let's put in the quantity u plus v. And so that equation becomes u plus v cubed minus 6 times u plus v plus 4 equals 0. This becomes u cubed plus v cubed plus 3uv times u plus v minus 6 times u plus v plus 4 equals 0. And so the high school algebra student in you has got to want to jump at that common factor of u plus v. So if we take u cubed plus v cubed plus a coefficient that looks like 3uv minus 6 times u plus v plus 4 equals 0, the idea is that we want to make that u plus v term go away. And so you can see here that what has to happen is to have 3uv minus 6, well, I'm going to write that 6 suggestively as 3 times 2. If we want that term to go away, that's going to imply that the product u times v equals 2. So in general, what's got to happen is that 6, well, where is that coming from? In the previous lesson, I identified the depressed form of a cubic as being x cubed minus 3p times x plus q equals 0. So in the equation that we're trying to solve here, for 3 times p to equal 6, notice the minus already matches, what we have to have is that p equals 2 and q equals 4. So what happens in general is once you identify what p is, then a constraint between u and v is that u times v has to equal p. It has to equal whatever is playing the role of p up in this equation. And so if we set u times v equal to 2, then the u plus v part here is going to go away because it'll have a coefficient of 0. And so what we'll have is an equation that involves actually two unknowns. So what we're left with is u cubed plus v cubed. Because my memory is very short, I have to go over here. The minus 6uv, or the 3uv minus 6 times u plus v goes away. And what we have is plus 4 equals 0, subject to the constraint that u times v is equal to p, is equal to 2. So we can use that relationship, thinking of this as a system of two equations in two unknowns. So we have one equation right here and another equation right here. We can solve this second equation to write v equals 2 over u. And when we do that, and then we substitute it into the other equation, what we get is u to the third plus 2 to the third over u to the third plus 4 equals 0. If we multiply through by u to the third power, this becomes u to the sixth plus, keeping it in order of degree, 4u to the third plus 8 equals 0. And so now what happens here? That looks like a much more horrible situation, right? You have now a 6th degree polynomial in this new variable u. But, well, a good question for Batman and Robin from the Riddler. When is a 6th degree polynomial not a 6th degree polynomial? Well, when it's really a quadratic polynomial in the variable u cubed. So that being a quadratic equation in u cubed, we can always solve a quadratic equation. We can set u cubed equal to the expression we'll get using the quadratic formula. So again, shrinking things down a little bit to avoid having to unnecessarily go to another page. Okay, what we know is that u cubed, the variable, is the negative of the linear coefficient, so it's negative 4 plus or minus the square root of that coefficient squared minus 4 times the leading coefficient times the constant term all over 2 times the leading coefficient. And so that becomes negative 4 plus or minus the square root of minus 16, because this is 16 minus 32 all over 2. Now, at this point, Cardano and his buddies were stuck because they lived at a time when the complex numbers had not yet been invented or discovered, depending on your philosophy of knowledge and life and mathematics. So, be that as it may, they were done. They actually had a fancy name for this. They would say that this cubic unfortunately fell into something that, well, they spoke Latin back there when they talked math, the casus irreducibilis. And so they'd be done with it. And so this particular equation Cardano couldn't solve. You see an example in the textbook of one done by Cardano's method that leads into exercise 5.3 and 5.4, and some discovery there that even when you have a nice root of the cubic, that Cardano's method can make it look really horrible. And here we don't have a nice root. So what are we going to do? Well, in order to finish this out, I'm going to go ahead and pretend like we can go back in a time machine and give Cardano the complex numbers. If we do that, then we're not done. We just write this as negative 2 plus or minus 4i over 2, negative 4 plus or minus 4i over 2. which reduces to negative 2 plus or minus 2i. So you actually have two roots here. Okay, so now what do we do? Well, let's go take a look. We have u cubed equals negative 2, let's take the plus case, plus 2i. We need to be able to find the cube root of this complex number. Now we'll see a method involving something called de Moivre's theorem in chapter 6 that allows us to do that. For the moment, I'm going to just pull it out of a hat. I'm going to go through and tell you what the cube root of that complex number is. So it turns out that if you take the complex number 1 minus I and cube it, that what you're going to get is, by the binomial theorem again, 1 to the third plus 3 times negative I times 1 squared plus 3 times negative I squared. There should be another parenthesis around that, so let's get rid of that mess. 3 times negative I squared times 1 plus negative I cubed. So we keep using that same idea with the binomial theorem for cubing a binomial. This becomes 1 minus 3i minus, because if we take I and square it, we get negative 1. So that's going to turn out to be minus 3. And then, if we take I and square it, we get minus 1 times negative I gives me plus I. And so, the real part, we get negative 3 plus 1 is negative 2. And then we have a minus 3i plus I is minus 2i. So that actually gave us the other value. Well, I can do calculation by erasure. Let's look at the case of u cubed equals minus 2 minus 2i. Note that that was the other choice here with the minus down here. So I've shown you how to find, or I've demonstrated that actually negative 2 minus 2i has a cube root. So this would tell me that u is equal to 1 minus I. Recall that v is equal to 2 over u. And so that would be 2 over 1 minus I. And from back in high school algebra, we learned that in order to rationalize the denominator on a fraction with a complex denominator, we multiply top and bottom by the conjugate of the denominator. And so what we get is 2 plus 2i. That looks familiar. And then here, by the difference of squares formula, we get 1, we get a minus I and a plus I from the inner and outer terms, and then minus I squared. This is 2 plus or minus 2i over 2, not plus or minus. I'm sorry, that is 2 plus 2i over 2, which is 1 plus I. That's for v. What do we know? That x has to equal u plus v. That was the substitution that we made. So that would be 1 plus I plus 1 minus I, which is 1 plus 1 plus I minus I, which is equal to 2. So now we actually have a cube root, or a solution to the equation. So Cardano couldn't have done that much, but what we did is we just produced a value of x that made the original equation equal to 0. So actually there's the original equation. We now know that x equals 2 is a root, so x minus 2 is a factor. And so if we do the division problem, x cubed plus 0x squared minus 6x plus 4 divided by x minus 2. Here's all this high school algebra coming up. You put an x up here, actually an x squared times x is x cubed, and then there's a minus 2x squared, and if we subtract, then what we get is x cubed minus x cubed is 0, and 0 minus negative 2x squared is positive 2x squared. We bring down the 6x, and then we do the same thing again. So x times what gives me 2x squared. I'll take 2x for 1,000. This is now 2x squared minus 4x. Subtract. Negative 6x minus negative 4x is negative 2x. Bring down the 4. And now we look at what do we multiply x by to get negative 2x. How about negative 2? And so what we get is minus 2x plus 4. And if we subtract, that's equal to 0. And so what we have is that our original left-hand side factors as x minus 2 times x squared plus 2x minus 2, and that's going to be equal to 0. That can happen in only two ways. Either x is equal to 2, which is the root we already knew, or x squared plus 2x minus 2 equals 0. Then what we wind up getting is x equals negative 2 plus or minus the square root of 4 plus 8 over 2. And so this is negative 2 plus or minus the square root of 12, which is 2 times the square root of 3 over 2. And so the other two roots are negative 1 plus or minus the square root of 3. And so that takes care of finding all three roots. The idea with Cardano is once you found one root, you can do division and reduce the problem to the quadratic formula. Now, let's not lose sight of the fact that Cardano couldn't have done this, and so Cardano is stuck at u cubed equals negative 2 plus or minus 2i because he didn't have the notion of I. And so the next demonstration will be based on the work of a mathematician by the name of Viète, and Viète's method will be illustrated. It is actually laid out with a few mistakes on pages 54 and 55 of the text. And so we'll run through that with this particular one and actually do a variation on what's in the text. We'll produce all three roots using, of all things, some trigonometry. So stay tuned for that part of the story in the next lesson.